Okay, last video on complex numbers. You're probably relieved, and this is about regions and relations on the Argand diagram. Okay, so right, and so what we're doing is we're going to have a look at some different relations and seeing how they relate to what it might look on the Argand diagram. The important thing to note here is that there's two ways to do it. You can do it algebraically, so if you love your algebra, that's a good way to do it, but they do become super complex. Or you can do it geometrically, and this tends to be much faster if you understand what's going on. So I'll talk about both of these things. Okay, I'm just going to go straight into some examples to show you what we're talking about. Okay, so first example, here is a relationship here. The imaginary part of some complex number z plus the real part of some complex number z is equal to 1. Okay, right. Basically, what we're looking at here is we're looking at the complex number x plus yi. This is the important step to remember at the start of any of these, and then you can figure anything out. Okay, so if you've got the imaginary part plus the real part, so what's the imaginary part of z? The imaginary part is y. So y plus what is the real part of z? The real part of z is x equals 1. Therefore y equals negative x plus 1. Okay, so this is the actual relationship if we think about it in terms of x and y on our graph. So if we just draw a very dodgy graph here, okay, what does that look like? It'll be negative x that's going down there and it's crossing at 1. So I've got 1 there, 1 there, and what that'll be, I should learn how to do straight lines, but anyway, that should be a straight line. My apologies. I'll learn how to do lines on this program, I promise. That is the relationship. So this relationship here gives all the points on this red line here. So that's your first example. So x plus yi is the key there. Let's look at another one. How about this one? An example where the argument of z is equal to negative pi on 6. Okay, so this is saying which, if you got all the numbers z that have an argument of negative pi on 6, what would that look like on an Argand diagram? And it would look like this. So if you got a small, with a small pi on 6, pi on 6, negative pi on 6, roughly here, so it'll be there, another point there, you might have a big radius out there, but basically what it consists of is all the points on this line here. So where that's negative pi on 6, and you get all these points along this line, and it goes out to infinity. And so how we write that is with a ray and with an arrowhead like that, because it just keeps going out and out. The only thing to remember about this is it does not include the origin there. Okay, so we draw a round circle around that. It does not include that y, because that point right in the middle could be any argument. We don't know what it is. It doesn't really have an argument because it doesn't go anywhere. So always put a circle in that when you draw a ray. So that's how we draw an argument. Just another example of an argument might be something like, what does this look like? Argument of z, pi on 2, something like that. What will that look like? So again, dodgy diagram. It's one of my better ones. The argument of z is in between 0 and pi on 2. Okay, so pi on 2 is out here, 0 is here, and so what that means is that I'll just stop. It doesn't include 0, so it's not going to include this line here, but it is going to include this line. So I'll do it in different colours so you can see. So it's going to include this line, but it's not going to include that line. So I'll just do a dotted line along there. And so it's all any z that has an argument between there and there. And so basically it means it's going to be everything in that region, okay, out to infinity. You don't draw that in there, but it's going to be all of this stuff there, okay, including that line, not including that line. So that's a couple of argument ones. Let's get to the meaty ones, okay. Okay, here we go. Let's have a look at what does this look like. Z minus 2i equals 1. Okay, so I've got the modulus of z minus 2i equals 1. Now again, algebraically, geometrically, which one should I do first? I'll do it algebraically. Right, here we go. Hard work. Let z equal x plus yi, and all we're going to do is substitute it in and solve it. Okay, so therefore, I'll go this way. I just need to use as much space as possible. X plus yi minus 2i modulus equals 1. I'll leave space there for the graph. Therefore, let's put the real parts in that. So let's take. No, I'll neaten it up for you. So real part is x, imaginary part I. I'll just put y minus 2, or like that, equals 1. Therefore, the square root of, so remember what a modulus means the square root of the real squared plus the imaginary squared. So that'll be x squared plus the imaginary y minus 2 squared is equal to 1. Therefore, let's just solve this now. Square both sides. X squared plus y minus 2, probably should have expanded there and then, equals 1. Therefore, expand this out now. We've got x squared. In fact, no, I don't want to do anything. I've just realised what I've done. We can stop right here. Okay, so what is that the equation of? So stop right there. You can see what that equation is. That is a circle. Okay, remember the formula for a circle is x minus h squared plus y minus k squared equals r squared. Okay, so this is a circle. Where is its center? Its center is at 0, 2, and it has a radius of 1. Okay, so let's quickly sketch that. So center of 0 and 2, so that's 2 there. That'll be the center. Radius of 1, so it'll come down to 1 and up to 3, and I'll just sort of sketch that around. That's not a bad circle, is it? So it will look something like that. That line around there, that circle, is this relationship here of z minus 2i equals 1. So that's how you do it algebraically. With algebra, how do you do it geometrically? It's really simple with geometric. What this is saying, remember what the modulus means. The modulus is just the distance. Okay, so what this is saying is that for each point z, the distance between z and 2i is equal to 1. Okay, I'll write that down. Distance between each point z and 2i is 1 unit. Okay, let's have a look at this graph. The distance between two, I'll get some red going here, the distance between 2i, so here's 2i here, okay, that's the point 2i, because this is the imaginary axis, that's the real axis, that's the point 2i. The distance between 2i and each of these points is equal to 1, because that distance is 1, that distance is 1, that distance is 1, wherever you go, that's the definition of a circle. And so if you can look at this and go, well, the distance between z and 2i is equal to 1, then you can figure out that's a circle. It's going to be a circle equidistant from 2i with a radius of 1. And so it's much faster just thinking about it and being able to draw that. But this is how you do it algebraically. Okay, one more example I think, and I think we're done. Okay, let's just look at this one, another example. Let's do modulus of z is equal to z plus 4. Okay, now geometrically or algebraically? Let's do it algebraically. I'll just do it geometrically. Let's have a think about this. What this is saying is the distance of z to 0, okay, the distance of z, remember modulus of z means how far is it from 0, okay, the distance from z to 0 is equal to the distance of z to 4, okay, where is 4 on here? Sorry, negative 4, z minus negative 4, so negative 4 is here, okay, so there's negative 4, and what it's saying is that, and here's 0, okay? It's saying that for each of these points Z, where is the distance to 0 the same as the distance to -4? Okay. Well, so let's try to pick a point that's the same distance from -4 as it is from 0. Okay. So right in the middle there, at -2, that'll be one. Okay. That distance there, I'll just draw this. This is saying that the distance from Z to -4 is equal to the distance to 0. Okay. That's what we're looking at. That's the one point there that we can choose. What other points will satisfy this? Well, how about here? You know, that distance there is the same as that distance there. How about up here? That distance there is the same as that. In fact, any point along this line here, it's a really good line, will satisfy that. Any point here will satisfy that. The distance from that to 0 is equal to the distance of that to -4. So that's geometrically. Let's see if algebraically this agrees. So let's let Z equal x plus yi. Therefore, I'm just going to do it real quick now. Modulus of Z is the square root of x squared plus y squared, and that's equal to the square root of, I'm going to put this straight in, hopefully you can follow me, x plus 4 squared plus y squared. Okay, now let's just solve this. Square both sides. X squared plus y squared is equal to x plus 4. Should have expanded there and then. Never mind. Therefore, y squareds cancel. They go. Okay. X squared equals x squared plus 8x plus 16. X squareds now cancel out, therefore we get, I'll bring the 8x, get negative 8x equals 16, therefore x equals -2. What does the line x equals -2 look like? Exactly that. So that's the line x equals -2 there. So that checks out with my geometric interpretation. So algebraically, geometrically much faster if you can figure it out.